In Python, the class system and much else is implemented using dictionaries. You can let the data lead the code. You can decide the behavior at runtime while the program is being used. So the type function gives you the type of an object, but there's another version which allows you to create a new type. So we're going to connect to another company and download their data, and we're going to make models of it dynamically. So let's say we make a new type and we call it Acme Broker. And then let's see what else we need. We need bases. Well, we don't need to inherit from anything. We have the dictionary of attributes and methods, and then we can do other things as well we don't care about. So like that, we can make it have a bit more to it. We can have some attributes. Let's have a name, and then by default, let's have nothing. And then let's have a function as well, greet them. And I could have just made the function with def, but I haven't, so I'll just do lambda self. Hey, self.name. So now I can go, Bob is an Acme broker. Name is Bob, bob.greet. Hey Bob. There we go. This one-liner that creates first-class type at runtime based on whatever variables we want to bring in. That is what you get with Python. For those of you who want to rewrite everything in Rust, rewrite this one-liner for me in Rust. You can't. Rust can't do this. C can't do this. This is a very simple example, obviously more simplified than realistic, but this is how a lot of systems work. Web frameworks, ORMs, machine learning, finance, DevOps, they do something like that underneath. They can generate classes and do metaprogramming, which is brilliant, which is a big improvement over what came before. But it's not free. It comes with an overhead. So what is that overhead? Well, there are different elements to it, but we're going to measure one. The dynamic attribute tax of Python models. What does that mean? Let me explain.
It's a stock exchange. There's no money you can steal.
Really? And why are you people here?
So here we have a tuple of stock symbols on the British Stock Exchange. Holdings, Marks and Spencer's, Sainsbury's, Tesco. Imagine we're a brokerage firm that's buying and selling stocks for our clients. We might have a trade object where we give an arbitrary ID to the trade. We have a symbol, which is one of the stock symbols. We have a price that we bought or sold the stock for. We have the quantity, how much we bought or sold, and we have when we bought and sold it. Then we're going to generate a load of trades. We're going to pretend that we have a lot of customers buying and selling, but we're just going to create them at random. And we're going to create an n number of them. And then we're going to look at how big one of these trade objects, call it plain trade, one of these plain trade objects, how big they are. So how much memory is being used by the plain trade. Then we're going to time how long it takes to make all the trade. We're going to time how long it takes to make them. And then we're going to read them all back. And to prove that we've read them all back, we are going to work out the total value of the trades that we've done in that trading day by timesing the price and the quantity. And we'll get the value of the total trades that were made. And then we're going to look how much memory doing all that used, and then we're going to print it out. So let's just start with 100,000 trades first. So the instance of our trade object is 248 bytes, and to create 100,000 of them took 1.3 seconds, and then to read them back took 0.07 seconds. Kind of random made up number figure is we did 25 million worth of business, and it allocated 31 megabytes of memory to do that. If this was a real system, there might be many ways you can improve it. You'd probably want a real database. You could use multi-processing, you could use async IO. For what we're going to do, we're going to make another copy of plain trade. And we're going to call it slotted trade. And we're going to put here slots equals the fields that we're using in the class over there. So we've got make plain trades, make slotted trades. Let's do plain trades equals make plain trades 5. These are our trades. We have 1905 of Diego at 906p, bargain compared to the real price. Then we got 1237 of Marks and Spencer's at 813, 763 of Arm at 1210. We've got 101 more of Diego, and then we bought 732 of JD Sports. So we've got our B trade object. So P trade has trade ID, symbol, price, quantity, and a timestamp. Those data attributes are stored in the internal dictionary of the instance, but some things are stored in the class. So the plain trade has a dict as well. So we've got the init method and the str method and various other bits are stored in the class, and the instance, the attributes of the instance, so the name of the attribute and data are all stored in the instance themselves. This is what takes up most of the space of the object of the instance. That's the classic, the normal Python instance. But then we've got these slotted ones as well. So slotted trades is make slotted trades, and we get 5 of those. And then for F trade in slotted trades, print S trade. We bought 757 of Vodafone at 606p. Bought some of this, Sainsbury's, Vodafone, Cardo. So if you look at how the S trade works, that's slightly different. The class, the slotted trade class, that has a dictionary. And if you see in the dictionary, it has the symbol, price, quantity, timestamp are stored in the dictionary. So if you looked at the normal one, that didn't have that. It didn't have anything about that. These names were just stored in the instance. So every instance has these attributes. So if you have 5 million instances, you have 5 million copies of these attribute names. Whereas with the slotted trade, it moves them into the class. And the deal is that if you add the slots to the slotted trade, you're promising never to change them. You're not going to do the dynamic changing of them. They're going to be fixed. Then when it reads in this slotted trade object, Python, instead of storing the attributes in a dict of the instance, it stores them in the class. When it interprets slotted trade, it creates a typed struct, which is like a C data type, struct of pointers to the data. And that struct has built into it these things. So it stores them in fixed memory locations. So it stores 4, and then that, and then that, and then that, and then that. It stores them. It has like a pre-made, like you can think of it maybe as like an array, but it's actually like the members of the struct are these values, which are then fixed in the struct. And then these have pointers to the objects. And this is a more efficient data structure than the Python dict, which is completely flexible and you can change it dynamically in real time. For the non-slotted, the plain trade, I can add extra whatever I want. I could add like customer equals Bob. Whereas if you promise not to do that, then you can use slots, and therefore all the instances will be the same. And as I said, when Python first reads this in and makes a class of it, it will create a struct that has the members. The members will be these. And if you don't understand what I'm saying, don't worry. You'll understand it in years' time if you're a beginner programmer. The slotted instance is like what in C++ or C would be a typed struct, where the instances are stored in a fixed memory location. Python, because it's dynamic, can't actually use a type struct because type structs are in it compile time. So it has this type struct called PyMemberDef, which does the same thing in a dynamic way. As it says here, an array of PyMember structures defines the name, type, and offset of selected members of C structures. So we have an array of PyMemberDef structures, and that works the same way as a type struct in C or C++. So for each field in the slotted class, we have a PyMemberDef struct. So when it reads in the class that has slotted on it, it looks at each field, and for each field, it makes a PyMemberDef. So it makes like a type definition of that field. And that field has a name, it has a type, and most importantly, it has an offset, so like how big it could be. This allows Python to implement basically a C struct for the instances. So for each instance of the slotted class, so it's the slotted trade, for each instance of the slotted trade, it knows that it has a price field, which is called price. It has a type, which is an integer, an offset, which is like the size of an integer, like 32 bits in Python. It will then allow it to read from memory exactly the same as a C struct would. So they've basically re-implemented the C struct. An area of continuous memory, like a C struct, it reads from it. So here's the code that reads from the slotted object. It will take that PyMember description, that PyMember definition here, and it'll take the object. This tells it where the object is in memory, and then it gives it that definition. So then when it does get one, it knows where the offset is, it knows how big it knows where it is, it knows what it's supposed to be, it knows how big it is, because of the definition in the PyMemberDef. Then it's got the object address, it's got the PyMemory definition. It can then, using the type and the offset, gets that value out of memory. And the same thing when you set a member of a slotted instance, called something like member set. There it is. It has the object, and then it has the value you want to set to the object, and then using the PyMemberDef struct, it then can find the right place to write the new value. So it writes the value at the right place because it knows the type and the offset, so it knows how big it is and everything. And then it goes to that memory location, and then the address in memory, you've got the PyMember definition, and then you've got the thing that you want to write to memory. So then it goes and writes it to memory. So so when you have a slotted instance, it makes an array of PyMemberDefs, which then it's like the type. It's like a type struct in C++, and then it uses that definition to write and read from the right place in memory. And each slotted instance is stored in continuous memory, exactly the same as like a C struct is. So the value will be next to the quantity, which will be next to the ID, and so on in memory, which is, it's the Python code, the CPython implementation here is kind of more complicated than just using the dict that's already defined, but it's much more memory efficient because it's much more lower level. Because the types of each field and because the names of each field and the types of each field and so on are stored in the PyMemberDef, they're stored in the class, not in the instance. Much simpler way to understand this is with a metaphor. Let's take 100,000 plain trade objects and write them to JSON and write them to CSV. So it's written them to trades.json and trades.csv. So if you look at trades.json, we have an object for each trade. Because the keys are represented each time, we could have different members on each object. So we could have extra fields, or we could change the fields. We can add extra information in here, and this would completely cope. This would still be, you can read it in with Python, read it out with Python, read it in with JavaScript, read it out with JavaScript, it'll be fine. If we look at the CSV, it gives you the column headers once, and then we have all the rows, and it never tells you the column headers again. The field names have been moved up to the top as column headers, and then you've just got the raw data from now on. So if we look at the file sizes, the CSV is 4 times more efficient than the JSON version. And this is a bit like the plain Python object, and this is the slotted Python object. The metadata are about field names and the field types, the size of the value, have all been moved to the class level, not at the instance level. So it's very memory efficient and small. So that's a performance upgrade. As I said, you want to be looking at databases, you want to be looking at async.io, you don't want to be looking at this. But the good thing about it is that it tells us the difference between a dynamic system and a non-dynamic system. The difference between this and this is the dynamic allocation tax. That's by being able to keep things dynamic and keep everything as dictionaries, it does use more memory than making everything static and just using a struct. So that's the difference between the two. So the plain trade is the dynamic one, and the slotted trade is the non-dynamic one. And the difference in space is, and the time it takes to use it, that's your dynamic allocation tax. Look at all the versions of Python we have. Can't use 3.2.6 because there's no tracemalloc module. We've got the same problem with 3.3.7 and the tracemalloc. So the earliest I can go back is to 3.4. Yeah, we start in 2014 with Python 3.4.10. So the size of instances, the plain dictionary-based object is 248 bytes. The slotted version is 80 bytes. The create and the read are not so different. I mean, it's marginally faster, the slotted version, but the memory used is absolutely massively different. 1,709 megabytes for the plain version, but the slotted version uses only 912 megabytes. So that's significant saving, and that's the dynamic allocation tax. So the dynamic allocation tax here is huge. Then we have 3.5.10. Everything's pretty much similar. Then 3.6, the amount of memory the dictionary uses goes down quite a lot. So the objects, the dictionary back, they drop from 248 to 184, which then leads to slightly lower memory allocation. I mean, we've gone down 300 megabytes, so that's pretty good. And the slotted is pretty much exactly the same. And then we get to 3.7, and that's pretty much the same as 3.6. And then we get to 3.8, and the size of the object falls again, and the amount allocated, the memory allocated, falls again, and the slotted fall as well. So the slotted and the dictionary backed in 3.8 fall quite a lot, and the memory used in both falls. 3.9 is much the same as 3.8, and then 3.10 is much the same. But then in 3.11, the size of the instances goes back up. The slotted stays the same, but the size of the dictionary-backed instance goes massively back up. Yet, the speed of everything goes massively faster. So the create of the dictionary-backed one goes from 13 to 9, but the slotted one goes from 13 to 7. And the amount of memory allocated in the plain goes much lower, but then the memory allocated by the slotted goes up. So they kind of meet in the middle. And then in 3.12, again, very close. And again, Actually, that turned out to be about the same speed. It's slotted. So even though this is still quite hefty, it's lost a few bytes, but it's still quite hefty, but it's still fast and, you know, quite light in overall memory allocated compared to where we started. So we started at 1700, and then we're down now to 1000. So we've lost a significant amount of memory allocated, with significantly less memory allocated. 3.13, it stays really fast create, really fast read, and then, yeah, not much memory allocated. And then in 3.14, it's also much the same. So there was a huge speed up with 3.11, and the memory usage has been coming down the whole time. So if we look at the memory allocated in the different versions, the slotted has remained the same, but the dictionary backed one has got more and more efficient and less memory needed to do it. I mean, that's hugely more efficient. So the same code, we haven't changed anything, but the Python developers have made the same code far more efficient than it was before. If we look at the difference between the two, so we minus the slotted from the dynamic, from the dictionary backed, then we get a graph like this. So the dynamic attribute memory tax, the difference between having a slotted struct and a dictionary, collapses over the version. When you're at 3.4 and 3.5, there's a huge tax in having dynamic objects, but then that collapses over the Python versions as the Python developers make it more and more efficient. So by the time you get to today, there's very little advantage in having a slotted object. The dictionary backed object is pretty much as efficient. I mean, it uses the same amount of memory overall, and so even this is way bigger. The individual instance is way bigger. The overall memory allocated is not much different. They're doing some clever stuff behind the scenes that basically gives you the advantage of slotted without using slotted. So there's basically no point in using slotted now. To be fair, I did say at the beginning it wasn't like a very popular optimization and not the most practical optimization in many cases, but it does prove that the cost of being a dynamic language is falling all the time. The difference between a static object representation and Python's dynamic objects is falling all the time. So that's really good, because if you write the code in 2014 and then in 2026 it's significantly more performant, it uses significantly less memory, so you can do more of them. To put it another way, the dynamic attribute memory tax from 2014 to today has dropped by 4 times. It stopped using 3/4 of the memory. It's pretty amazing, pretty amazing. And the thing is, when you write Python, you're writing an interpreted language. You're writing a language which is written to it's a specification. You're writing to a specification, and then that's interpreted into bytecode and then executed. So it's not low level, wide into the memory. Behind the scenes, the Python developers can change how it's implemented and give you massive improvements. So, so this will go on. So the code you write now will become more performant and faster in the future as they keep improving it. Whereas if you write your code in C or Rust, it will be fast now, but because it's low level doing it in the machine, it won't ever really change. It won't ever really, there's no way they can really speed it up. They can make maybe they can make the compiler a little bit more efficient, but Python, because it's a high level language and it's interpreted, they bring in quantum computers and then the same code can run on that and then be interpreted into something else. Thanks for reaching the end. Please like, subscribe, it really helps. Maybe not in the way you think. It's a new channel, so I really need subscribers. Press the subscribe button, which is more recommendation button. It doesn't actually guarantee that YouTube shows you my future videos, but it suggests a gatekeeping model that people with similar interests to you might like my future videos. Also encourages me to make more videos if you do, so subscribe, come back for more next week. And watch my old videos, which are really good.